Today we're going to talk about the rational root theorem, and we're going to start with this polynomial that's in general form. This polynomial that I have written down represents any possible polynomial. The rational root theorem says that if I want to break this polynomial down, if I want to factor it, I can do so by first identifying all of the possible rational roots of the polynomial. I do that by first making sure that my polynomial is in standard form. That means it has to have descending order of exponents. Right now my polynomial is in standard form because we can see that this is descending order of exponents. N is larger than n minus 1, which is larger than what comes after it. On the end we have x to the first, and then that a naught is the constant term. The rational root theorem tells me to first list all of the factors of our constant term, which in this case is a naught. Then I take all of the factors of the lead coefficient, which in this case is a sub n. The ratio of the factors of the constant to the factors of the lead coefficient give me a list of all of the possible rational roots for this polynomial. When you see this in a textbook or another source, you may see this written as a list of p's and q's, where p's are all of the factors of the constant, and your q's are all the factors of the lead coefficient. You have to take each p-value and divide it by each q in order to get your full list of possible rational roots. Let's take a look at an example now and test this out. For this polynomial, I'm going to follow those steps I mentioned earlier. First, I want to make sure that the polynomial is in standard form. In this case, my polynomial is already in standard form, so I'm good to go. The second step is to create the list of p-values. And remember, p-values are all the factors of the constant. In this case, my constant term is 42, or you could think of it as negative 42. Whether you call it positive or negative, your list of p-values should be the same. So my p's are all of the factors of 42, keeping in mind that they could be positive or negative. Next, I want to list all q values, which are all of the factors of the lead coefficient. In this case, my lead coefficient is 1. So the only factors that I'll have for my q's are positive and negative 1. Once I have my p's and my q's, I'm going to list all possible rational roots by dividing each p by each q. In this case, because my q's are just positive and negative 1, this is really just a repeat of my p's list. This list represents all of the possible rational roots of this polynomial. It doesn't mean that these are all of the roots of this polynomial. It just means that if it's a root that's rational, it will be on this list. In order to tell which of these is actually part of the roots for this polynomial, I have to test them. So you can test them using synthetic division, or you may be able to use your calculator to test them also. For right now, I'm going to test using synthetic division, and later I'll show you an example that uses your calculator. So our fifth step is test the possible rational roots. I could choose any of the roots on this list to begin my test. So I'm going to start with 6, and I'm going to set up my synthetic division. Remember, when you're doing synthetic division, you're looking for a remainder over here in this box of 0. That tells you that this is in fact a root of this polynomial. So I'm finding that I have a remainder of 178. This means if I had plugged 6 in for x in this polynomial, I would get 178 out. This is telling me that 6 is not a root of this polynomial. However, our synthetic division wasn't entirely in vain. I noticed that that bottom row of my synthetic division has all positive numbers, which tells me that 6 is an upper bound for my possible rational roots. I can get rid of any of the other rational roots that are greater than 6 because it is an upper bound. So that means I can cross out positive 7, positive 14, positive 21, positive 42. And I've just narrowed my list down. If I had found that my last row contained alternating signs, if it had gone plus minus, then I would have found that that number was a lower bound and thus been able to cross out any numbers that were less than that value. Keep this in mind if you have a really long list of roots and you have to do this by hand. If you see all positives, don't try any numbers larger than that number. If you see alternating signs, don't try any numbers smaller than that number that you were testing. So I need to choose another number to test. I'm going to go on the opposite side of my list this time and try -7. And again, I'm looking to find a remainder of 0. That's what's going to tell me that I've found an actual root of this polynomial. And in this case, -7 is a root of the polynomial. This means now that I can break it down a little bit. I've factored my polynomial a little bit. Remember, our original polynomial looked like this. And when I divided that polynomial by x plus 7, it came out evenly. And I was left with x squared minus 4x minus 6. Looking at x squared minus 4x minus 6, I see that this does not factor further. So I have now fully factored this polynomial. So now let's look at another example. Again, I'm going to use the rational root theorem to factor this polynomial. I'm going to start by listing my p's, which again are the factors of our constant term. In this case, our constant term is 9, and our lead coefficient is 2. So I'm going to write down a list of the factors of 9. And then I'm going to write the list of the factors of our lead coefficient 2. To get my list of possible rational roots, I'm going to take each of these p-values and divide them by each of the q-values. So I'm going to start with my p's and divide each of them by 1, because that's the first value on my list of q's. Now I'm going to take each of my p's and divide them by 2, because that's the second value on this list of q's. And now I have my complete list of possible rational roots. And I need to go into the phase where I test these possible rational roots to see which ones are actually roots of this polynomial. This time I'm going to do that test on my calculator. So the first thing that I need to do is put the polynomial function into y1. Once I have that function in y1, I want to check my table settings and make sure that independent is set to as. Then I'm going to go to my table, and I'm going to start plugging in the list of values for my possible rational roots. We can see that -1 is an actual root of this polynomial. So I'm going to go back, and I'm going to use -1 in my synthetic division to break this polynomial down. And my synthetic division does confirm that this is a root of the polynomial. So we've taken our original polynomial and divided it by x plus 1. It divides evenly into the original, and what we're left with is 2x cubed minus x squared minus 18x plus 9. So now I'm going to go back to my calculator and plug this function into y1, and then I'm going to go back to my table to test the rest of my list. I want to test -1 again, just to be sure that it's not a double root. Here I'm seeing that both -3 and 3 are roots of this new polynomial, the 2x cubed one. So I'm going to go back and I'm going to do synthetic division using -3 this time. And I'm going to do this synthetic division on the new polynomial, because now I'm trying to break this down. So this is all part of the factored form, and I'm trying to further factor this polynomial. So we have started with this factored form from our first round of synthetic division, and then we divided that second term by x plus 3. We found that it divided evenly, and we were left with 2x squared minus 7x plus 3. Now I'm seeing that this is a quadratic. You can factor this using your traditional factoring methods. So if you see an easy way to factor this, go ahead and do it. You don't have to continue using the possible root. I remember from looking at the calculator that 3 also worked in this other polynomial. So I'm going to get test 3 out in synthetic division on this remaining term. And that's a quick way to factor, especially when a is not 1. So I divided that by the factor x minus 3 and found that it divided evenly. leaving 2x minus 1. So now I've fully factored this polynomial that we started with. Now, what I want you to do in your discussion boards is answer two questions. The first question is, why is it important to factor polynomials? And the second question is, if you're using the rational root theorem, you test all possible rational roots, and none of them work, what does it mean? So I want you each to post on the discussion thread with an answer to these two questions. Then I want you to respond to at least two of your peers' ideas.